The purpose of this discussion is to tie together the different concepts that we've described to go over the and outline the journey that you would take if you were given a problem, like some kind of situation where you have a geometry and you're given the potential at those different geometries, to use that to find the electric field. And then once we have the electric field, remember we can use the boundary condition with the normal vector to use the fact that n dot, the electric flux density, is going to give you an expression for the charge density. And once you have the charge density, you can then arrive at the capacitance that is in the system and ultimately find out how much electrostatic energy can be stored in the system as described. So these are all quantities of interest that you would need to find, and usually you would be given the potential as a starting point because that's often the easiest thing to measure. And so I would want to tie all the concepts together to show you how you can go from this initial piece of information to find all the other quantities of interest in an electrostatic field scenario. The first step, we use one of the tools that we most recently learned, is if you're given a region, let's say you're given two surfaces here, you're told that this is equal to V naught and the potential here is equal to 0, and you want to find out what the field is in your region of interest. One of the ways that you can find that is you apply the fact that the Laplacian of the potential is going to be equal to 0 everywhere in this region of interest, everywhere where there's no charge. Right, so you're given these boundaries, you want to find out what the in-between situation is, and you can use the Laplacian to find that. So with that, you will need to integrate twice. And so if you had to do this in a class, pencil and paper exam or homework type situation, you'll be given a situation where you can integrate this symbolically. But when you do this symbolically, you're going to have constants. Right, so use constants when you do your integrals k1, k2 as needed. So this is kind of like a second derivative. So you're going to do two integrals, and each time you integrate, you're going to be given a constant. Right. So how do you find the constants? Well, these constants are defined by the initial conditions or the boundary conditions. Right. So if I was given you basically what I'm saying is if you solve the Laplacian, you kind of have an outline of where's uphill, where's downhill, and so on and so forth. But you can't map that to actual elevation values unless you were given some boundary conditions. So you would then, if we call this location A, and if we call this location B, once you have this expression, you can use the boundary conditions. So applying that VA is going to be equal to, let's just call this VA and VB, just so that we're not setting one to be equal to 0. You can set that VA is going to be equal to one value, and then all the potential at this other location is going to be this other value, and you can use that to tease out your constants. And that gives you a complete answer for the potential V. Right, so now we have V. Next up, what you can do is you want to find the electric field. And how do we do that? That's right, we just take the gradient. Right? So the electric field is going to be equal to negative the gradient of V. So you can then use that to find your electric field. Next up on our list of quantities to tackle would be the charge density. So the charge density, rho s, how do we find that? That's right, we would use the boundary conditions. Right, so for each boundary, we can find the charge density by using the fact that rho s for that particular boundary is going to be equal to ni dot d. And remember, d or e, or you can also find d is equal to epsilon e. Remember that d is a vector function, right? So you have to put in a location to get the vector of interest. So you would evaluate this at boundary I, and so on and so forth. So you would apply this to each of your boundaries that you're interested in finding the surface charge density for. And remember that if this dot product is something unwieldy, you can also intuit your way out by just finding the component normal. That's normal to the boundary, right? So if you had an electric flux density that was in cylindrical coordinates, but you knew that your surface ran along the rho direction, then you can just extract the rho component, so you don't have to worry about this dot product. My point is, once it's in electric flux density form, you can use that to find the surface charge density. Now we have the surface charge density solved, so marching on in our warpath to victory. Next up, we want to find the capacitance. So to find the capacitance, recall that it's the total charge divided by the potential that was needed to create that. In the case of if you have the surface charge density, you can then use the surface integral of the surface charge density to find as one way to find the total Q, and then divided by the potential, and then you can use that to find the capacitance. Note that sometimes you may need to find capacitance per unit length. So you would make your adjustments to V or to your definition of V or the calculation of Q. Otherwise, if you were told to find capacitance per unit length, looking at that coax cylindrical coordinate example is probably the most straightforward, where we had this is the cross section of a coax that's coming out of the page, and you might be told that this is a length L, and you want to find the total capacitance, or you might just be told to find the capacitance per unit length, in which case you don't worry about any kind of calculation in the L direction. But the point is, you have the surface charge density, you plug it in here to find the total charge Q. If you keep things symbolically, it will have some relationship to V, and once you do some simplification, you will come up with your general expression of capacitance or capacitance per unit length, depending on what you're asked for. And then finally, from there, you can find the electrostatic energy density. And to do that, you just have to use the fact that if we define this at a point level, so for a very specific location, it's going to be 1/2 epsilon E dot E. You can then do the volume integral of both sides to find the total amount of energy stored. So uppercase W of E is just going to be equal to the volume integral of lowercase e. And that will allow you to find the capacitance and the total energy stored. As a quick summary, I just wanted to tie together the overall journey that you would take from given the usual measurable quantities that you would have, namely the potential at all the locations and boundaries, going all the way from that to finding the capacitance of the system and the amount of energy stored. And using that, I think the new piece of information that I'm introducing is the fact that you can use the Laplacian for any region where there isn't charge, and use a double integration, keeping the constants in line, and then plugging in the potentials for the known locations to come up with a full solution for the potential everywhere. But then after that, the process is very similar to what we've discussed before, where you find the gradient in order to get the electric field and electric flux density, use a boundary condition to get the surface charge density, which will allow you to find the total charge and therefore the capacitance, and then that also gives you the ability to find the total amount of energy stored. And so this process is kind of elegant. It basically ties together all of the concepts that we've gone over so far throughout the first few chapters, and is a good wrap-up of the electrostatics portion of the discussion for this class. So yay, all done with electrostatics.